Let's continue our lecture video in integral calculus. And here we are now on example number 6. Now let's try for the power formula again. So let u is equal to sine 3 theta, and derivative of u will be equal to cosine 3 theta d becomes 3 d theta, and that becomes equal to 3 cosine 3 theta d theta. Now if we follow the pattern, that becomes sine 3 theta, and the derivative here is du here is 3 cosine 3 theta d theta. Now, if you look at this closely, we did not go back to the given because there's no cosine 3 theta in the given. Therefore, we will disregard this. This is wrong because we will not be applying the power formula on this example. So, we will erase this one. So what can we use if we are not using the power formula? Now we will be using the trigonometric functions here. Since the given is integral of sine 3 theta d theta, therefore the pattern that we will use here is the integral of sine u du. So if we go back here, the pattern here that we chose is integral of sine u du. The answer will be equal to negative cosine u plus c. Before we proceed to the answer, we need to satisfy first this pattern here. So our u here, we will let u is equal to the angle 3 theta, and the derivative of 3 theta is 3 d theta. So if we use the pattern, we have the integral of the sine and the u we used here. So we have here sine, then the u and the du. So sine u is 3 theta, the du is 3 d theta. Now since in the original or the given here is we don't have the 3, we will then balance it by putting a 1/3 outside the integral sign so that we can cancel this out and go back to the given. Okay, then we can now disregard this portion here and focus here only. So since we were able to satisfy the pattern, let's now go to the pattern for the answer. So the answer here is 1/3. The negative cosine u here is 3 theta, then plus c. So the final answer here is negative 1/3 cosine 3 theta plus c. So that is for number 6. Now if we check this by differentiation, let's check it first before proceeding to the next. So we have here checking by differentiation, derivative of 1/3, so cosine 3 theta plus c, so that is negative 1/3. Derivative of cosine 3 theta is negative sine 3 theta, and the derivative of 3 theta is 3. Then derivative of c, or the constant here, is 0. So the final answer is so negative times negative, positive. So we have there 3/3 sine 3 theta, and then the final answer is sine 3 theta. So that is the given. We were able to go back to the original form. Therefore, the answer here is correct. Let's go for example number 7. So if we let here u is equal to cosecant 2t, so using the power formula, we're trying to use here the power formula. The derivative here will be, so what's the derivative of cosecant 2t? That is negative cosecant 2t cotangent 2t and then 2 dt. There's no cotangent in the given, therefore we will be disregarding this. We are not going to use the power formula. Therefore, again, just like we did with number 6, we will go and use the pattern for trigonometric functions. So since the given is cosecant squared 2t, therefore what we are going to use here as a pattern is this. Integral of cosecant squared u du is equal to negative cotangent u plus c. So let's assign u here as the angle 2t. The derivative of u is equal to 2 dt. Now let's copy the pattern here. Copy cosecant squared. Put u here and then the derivative of u. So that is equal to, so we have the integral of cosecant squared. The u here is 2t. Du is 2 dt. Now almost to the given, except we need to balance it with the constant 2. So we have here 1/2 outside. Disregard this portion. It's equal to 1/2. Then use the pattern. The answer for the pattern for the answer is negative cotangent u, which is 2t, plus c. So the final answer is negative 1/2 cotangent 2t plus c. Checking. By differentiation, we have their derivative of negative 1/2 cotangent 2t plus c. So that is equal to negative 1/2. Derivative for cotangent 2t is negative cosecant squared 2t. Then the derivative of 2t is 2. Then derivative of c is 0. So that is equal to negative times negative, positive. This is 2 over 2 cosecant squared 2t. So cancel, what's left? Cosecant squared 2t. So this is the same as the given, therefore the answer here is correct. So that's for number 7. Let's proceed to number 8. Integral of secant 1/2 z tangent 1/2 z dz. Again, let's attempt to use the power formula. Let u is equal to secant 1/2 z. So the derivative of secant is secant 1/2 z. Tangent 1/2 z, then we have 1/2 dz. Okay, so if we use the pattern, so it looks promising. Let's see. If we use the pattern here, we copy the u. So u here is secant 1/2 z. That's the u, right? Then the derivative of u, secant 1/2 z, tangent 1/2 z, 1/2 dz. So that becomes secant squared 1/2 z, tangent 1/2 z, then that is 1/2 dz. Well, we don't have squared of secant in the given, so let's not continue because this is already wrong. So this portion is already wrong. Okay? So again, since we cannot use power formula, let's use the trigonometric functions. The formula for trigonometric functions. So the pattern for secant, so the given is secant tangent. So do we have a pattern for secant tangent here? Yes, we have here a pattern for secant tangent here, this portion. Integral of secant u tangent u du is equal to simply secant u plus c. Okay, so that's the pattern that we're going to use. Secant u tangent u is equal to secant u plus c. Now notice that there's already a secant u tangent u here. The given already has secant u tangent u here. And what's missing is what's the du. So our u here, or what we let as u, will be the angle 1/2 z. So du here becomes 1/2 dz. Now if we substitute it with the pattern, becomes integral of secant 1/2 z tangent 1/2 z, because the u here is 1/2 z, and then the derivative of u is 1/2 dz. And then to balance it, because in the given there's no 1/2 here, so we will put a 2 outside the integral sign, so we can cancel out 2 and then go back to the given. Disregard this one, so let's focus here. So this one is 2, and then the pattern for secant u tangent u is secant u only. So secant of 1/2 z plus c. Okay, so that's the answer. Checking, let's see if what we did is correct. Checking by differentiation, we derive here. So ddz of 2 secant 1/2 z plus c. So that is equal to 2. What's the derivative of secant? So the derivative of secant here is secant 1/2 z tangent 1/2 z, and then we have here derivative of 1/2 z is 1/2 dz. Or 1/2. I just put it as 1/2. Plus derivative of c is 0. So that is now equal to 2/2 secant 1/2 z tangent 1/2 z. Cancel out, so what's left is secant 1/2 z tangent 1/2 z. So you can see here it's the given. That means the answer here is correct. Now what if we let u, how about if we let u here is equal to tangent 1/2 z. The du here is secant squared 1/2, then 1/2 dz. So no, still no, we're not going to use power formula. So that is number 8. Okay, let's go to number 9. Integral of cosine ln x over x dx. So obviously, ln x here is the angle for cosine. So let's attempt to use the power formula. Let u is equal to cosine ln x. du is negative sine ln x, and the derivative of the angle is 1x. Ln x, derivative of ln x is 1 over x dx. So there's no sign here in the given. Therefore, again, we will not be using your power formula like we did in the previous videos. So here, what we're going to use is the trigonometric functions formulas here, the patterns here. So the pattern that we're going to use, since the given is cosine, the first one here. Integral of cosine u du is equal to sine u plus c. So integral of cosine u du is equal to sine u plus c. So let u is equal to ln of x. So the derivative here is 1 over x dx. Then let's follow the pattern here. Rewrite cosine, put the u and the du. So integral of, rewrite the cosine, the u, which is ln x, and the du is 1x dx. Is this still the same as with the given? Yes. So cosine ln x, and this portion here, the x here and the dx, is actually 1 over x dx. So they're still the same. So since the du is 1 over x dx, so that is our du, we will disregard this portion here and then follow the pattern for the answer, and the answer is simply sine of u. So the answer is sine of u plus c. Sine ln x plus c. Now checking, let's see if what we did is correct. Checking by differentiation, d dx sine ln x plus c, that is equal to, derivative of sine ln x is cosine ln x, and the derivative of the angle ln x, that is 1 over x, plus derivative of c or constant is 0. So the final answer is cosine ln x over x. So we were able to go back to the original form. That means the answer here is correct. So that's for number 9. Let's go to the number 10. Again, let's attempt for a power formula. Let let u is equal to tangent 6y, and that is equal to the derivative of u is secant squared 6y and then 6 dy. There's no secant squared in the given, so we will not be using again the power formula. Okay, so again we will be using the trigonometric functions here. Since we have a tangent squared as the given, so tangent squared 6y, let's find here if there's a tangent squared here. There's none. Only secant squared u, cosecant squared u. There's no tangent. So the only tangent here is the one with secant u. So how are we going to solve this one? If there's no tangent u here, if there's no tangent squared u here, so what other method are we going to use? We're going to try if we can use the identities. So let's attempt to find the identity that has tangent squared. So how do we solve for the other two Pythagorean identities given this? Sine squared theta plus cosine squared theta is equal to 1. If we divide each term with sine squared theta, sine squared theta, and then sine squared theta, what happens here is that this becomes 1 plus what is cosine squared theta over sine squared theta? That is the inverse of tangent, which is cotangent squared theta. What is 1 over sine squared theta? That is cosecant squared theta. How about if this portion here, okay, if we divide all terms with cosine squared theta, cosine squared theta, cosine squared theta, what will happen? The answer will be, so what is sine squared theta over cosine squared theta? That is tangent squared theta plus cosine squared theta divided by cosine squared theta, that is 1, equals, what is 1 over cosine squared theta? That is secant squared theta. The third identity here has tangent squared theta. So let's use this. So that is tangent squared theta is equal to secant squared theta minus 1. So let's substitute it here. So this given here is similar with secant squared theta minus 1 dy. But since the theta or the angle here is 6y, so we will put here 6y minus 1 dy. Distribute. So we have there integral of secant squared 6y dy minus integral of dy. Now, do we have a secant squared in the patterns? Yes, we have. It's secant squared u du, that is equal to tangent u. So let's use this pattern here. Okay, so let u is equal to 6y. Derivative of u is 6 dy. Using the pattern, that is equal to integral of secant u, and then the dy, the du here is 6 dy. And since there's no 6 in the original here, so we will balance it with 1 over 6 and then disregard this portion, and the final answer here is the pattern tangent u plus c. So the answer here is 1 over 6 tangent u, which is 6y. How about this portion here? Remember that this portion is already solved in the power formula. So that is here, it is negative, this is already integral of y raised to 0 dy, and then that is the pattern for the power formula is y raised to 0 plus 1 over 0 plus 1. Then don't forget plus c. So that is equal to 1 over 6 tangent 6y minus is equal to y over 1, or that is y plus c. So that is the final answer. Now checking first, before we proceed to the next, let's check by differentiating. So checking. So the derivative of the answer 1 over 6 tangent 6y minus y plus c is equal to 1 over 6. What's the derivative for tangent 6y? That is secant squared 6y. Then the derivative of 6y is 6. Derivative for y is 1. Derivative for constant c is 0. So that is equal to 6 over 6 secant squared 6y minus 1. Cancel out. So we have there secant squared 6y minus 1. Or that is tangent squared 6y. So we were able to get back to the given. That means this answer here is correct. Let's go to the last one, number 11. Now for number 11, we have here integral of cosine squared y dy all over 1 minus sine y. Okay, so it's understandable if it's kind of scary because there's a lot of going on here. But if you look at this closely, we might as well try again the Pythagorean identities. Remember that we use sine squared theta plus cosine squared theta is equal to 1 a while ago to derive the Pythagorean identity for tangent squared theta. Now this time we will be trying to substitute cosine squared y with sine. So we have here cosine squared theta is equal to 1 minus sine squared theta. Let's see what we can do here. So we have here 1 minus sine squared y dy over 1 minus sine y. Still not going somewhere. How about if we expand this portion here? How? So what is 1 plus sine y? 1 minus sine y. So we have there 1 negative sine squared y sine y negative sine y. So if we expand this, the answer here is, we multiply this, the answer here is 1 minus sine squared y. So here, this is 1 minus sine y, 1 plus sine y dy over 1 minus sine y. So we can cancel this one out. And what's left here is 1 plus sine y dy. Distribute this. We have integral of dy plus integral of sine y dy. So for this portion here, this is integral of dy. We have already solved this as y. And for integral of sine y dy, using the pattern for sine, so well, that is already okay. So for integral of sine u du, the answer is negative cosine u. So here the answer will be negative cosine u, which is the y, plus c. So the final answer is y minus cosine y plus c. So that's the final answer. Now for checking by differentiation, let's see if what we did is correct. The y here, y minus cosine y plus c is equal to, derivative of y is 1 minus derivative of cosine y is negative sine y. Derivative of c constant is 0. So the final answer is 1 plus sine y, which is equal to this part here. So the answer here is correct. So that is for number 11.